who is from the Institute of Atmospheric Physics in China. And he's going to be talking today about robust changes in the global subtropical circulation under greenhouse warming. Over to you, Sijie.
Thank you. I'll share my slides first. I think there's some problem, and maybe you help me to open the slides. Oh, okay, thank you. And good morning, everyone. I'm Sijie Zhou from the Institute of Atmospheric Physics, Chinese Academy of Sciences. It's a great honor to be here and have the opportunity to share my research with all of you. Today, I'm going to talk about our recent study about the changes in subtropical circulation under greenhouse warming. Next slide, please. You might be wondering about the topic of this talk, subtropical circulation. Why should we care about it? And why are its changes on the global warming important? Our recent published paper in Nature Communications tries to answer these questions. To better understand the context of this research, I need to start by introducing the monsoon. Next slide, please. Monsoon is traditionally defined as a seasonal reversing wind accompanied by corresponding changes in rainfall. There is also the concept of global monsoons defined by rainfall patterns. This figure shows monsoon regions defined by the difference in rainfall between summer and winter. Clearly, East Asia is a very typical monsoon region. The East Asian summer monsoon brings water vapor from ocean to land. Next, please. In the annual cycle of East Asian rainfall, there is a clear onset of the rainy season marked by a rapid increase in southerly winds as the red arrow shown in the figure. These southerly winds can push the rainfall further north into East Asia. Therefore, it's easy to link the movement of the rain belt to the evolution of the East Asian summer monsoon. Next, please. To evaluate the impact of global warming on the East Asian summer monsoon, previous research created a summer monsoon index to measure the intensity of southerly winds from 1950s to the present. This index shows a significant weakening only in the late 1970s. However, East Asian rainfall experienced several interdecadal changes during this period. The different trends between the East Asian summer monsoon and rainfall suggest that it's challenging to assess the impact of global warming on the East Asian summer monsoon based solely on observations. Next, please. So, many studies have turned to the CMIP model outputs to explore the changes on the greenhouse warming. Another study evaluated the East Asian rainfall changes using warming scenarios from the CMIP models. Each bar in the right in the figure on the left represents a model result. Most models show an increase in East Asian rainfall. The rainfall changes can be further attributed to different factors. The increased East Asian rainfall is mainly due to the increased moisture in atmosphere, while the most uncertainty in rainfall change is from the circulation change. Next, please. A recent study focused mainly on low-level circulation changes in the Asian monsoon. The researchers used 3 indices to evaluate these changes, and all the indices indicate that the East Asian summer monsoon will strengthen while the South Asian summer monsoon will weaken. It's interesting to consider why the East and South Asian summer monsoons show opposite changes under global warming. Next slide, please. The response of monsoon circulation to greenhouse warming can be further split into fast and slow response, each driven by different mechanisms. These 2 responses have opposite effects on the East Asian summer monsoon. The fast response strengthens it, while the slow response weakens it. For the South Asian summer monsoon, both response leading to weakening. Therefore, this raises 2 important questions. Are the circulation changes in the East Asian summer monsoon regionally or seasonally dependent? And are these circulation changes consistent with global subtropical circulation changes? In the following talk, I will introduce how we address these questions. Next, please. In this study, we used multiple experiments from the CMIP 6, most of which are under warming scenarios. Thanks to the various scenario experiments provided by the CMIP program, we are able to validate the physical mechanisms in different aspects. We also use 5 single-model initial condition large ensembles to evaluate the impact of internal variability. Additionally, 6 experiments from the database for policy decision-making for future climate change are used to examine the uncertainty in SST warming pattern. We also built an intensity index to assess the changes in subtropical circulation by projecting these changes onto the related climatologies. Here is a simple schematic of the projection. To get the length of vector x in the direction of y, we project x onto y. Later, I will explain why we use the projection instead of other methods. Next slide, please. In our study, we represent the low-level subtropical circulation by 850 hectopascal stream function, which is calculated from the horizontal winds. The shading in the figures shows the changes in subtropical circulation, while the black contours show their climatology. By comparing these two figures, we see that both the changes and climatology of subtropical circulation vary with different seasons and regions. Measuring the intensity change in subtropical circulation becomes a challenge. Therefore, we built the intensity index mentioned earlier to quantify the change. Next slide, please. In the projection method, the time range is from January to December, and the spatial range is from 10 to 45 degrees latitude on both hemispheres. In this figure, each point represents the intensity change in a different model, and the different colors represent various warming scenarios. The cross markers represent the average of all model results corresponding to each color. We can ignore the details here and focus on the fact that most models in the warming scenarios indicate a weakened subtropical circulation. There is a clear linear relationship between the weakening of subtropical circulation and global surface warming. Next slide, please. We can obtain an intensity index based on global range through projection, and we can also get the intensity changes for each month and at each latitude. As shown in the figure on the right, the intensity change under the SSP 58.5 in the northern and southern hemisphere are quite different. In the northern hemisphere, it weakens outside of summer and is only significant in autumn. In the southern hemisphere, the subtropical circulation weakens north of its center and strengthens south of the center, resembling a poleward shift. Next slide, please. We can separate the intensity change in global subtropical circulation into the northern and southern hemispheres. The results are more pronounced. The figure on the left shows the result for the northern hemisphere, while the figure on the right shows those for the southern hemisphere. The weakening in the northern hemisphere is stronger, but the changes in subtropical circulation are insignificant in the southern hemisphere. Next slide, please. As the internal variability can greatly influence the circulation change, we used 5 single-model large ensembles to check the impact of internal variability on the subtropical circulation change. The results on the warming scenarios of these 5 large ensembles are shown as the gray hollow markers in the figure. 4 out of 5 large ensembles show a weakened subtropical circulation with a limited role of internal variability. Therefore, the impact of internal variability on subtropical circulation changes seems to be relatively small. Next slide, please. As mentioned in the previous study, we can also separate the subtropical circulation changes into components related to different mechanisms. Among the many mechanisms related to the greenhouse warming, 2 major ones are the uniform SST warming and the CO2 direct effect. The figure in the top right shows a significantly weakened subtropical circulation induced by uniform SST warming, which exists throughout the year. In comparison, the CO2 direct effect strengthens the subtropical circulation mainly in boreal summer. The sum of the responses induced by these two mechanisms resembles what we see in the warming scenarios shown earlier. Next slide, please. And besides this, another important mechanism is the SST warming pattern. We evaluate its effect based on the related CMIP experiments in the CMIP. The figure in the top right shows an insignificant impact of SST warming pattern. However, all the models are forced by the same pattern SST warming, without considering the uncertainty in SST warming pattern among different models. Next slide, please. The experiments from the database for policy decision making for future climate change give us a chance to evaluate the uncertainty in SST warming pattern. It provides 6 simulations forced by 4K pattern warming as shown in the figure, and which are skewed from 6 representative SST warming patterns extracted from the CMIP models. Next slide, please. The purple crosses in the figure on the right show the result from this 6 simulation. Let me magnify the result a little bit, and please, yes. The responses range from 0 to -7%, showing a considerable spread, but most indicate a weakened subtropical circulation. It is difficult to attribute all the intermodal uncertainty to the SST warming pattern, although it does play a large role. Next slide, please. And finally, we use the abrupt force CO2 experiment to examine the timescales of subtropical circulation changes. In this experiment, the CO2 concentration is quadrupled compared to the pre-industrial level in the first year and then keep constant for 150 years. We can see that the subtropical circulation initially strengthens and then gradually weakens with increasing global warming. It's clear that the timescales of direct CO2 effect is very fast, while the effect of greenhouse warming can last for a relatively long time. Next slide, please. At the end of the presentation, I should answer the questions posed at the beginning. The intensity changes in the East Asian summer monsoon are consistent with the intensity change in global subtropical circulation. The global subtropical circulation will eventually weaken, driven by global warming and partially offset by the CO2 direct effect. Next slide, please. And that's all for my talk. If you are interested in our study, please refer to our paper published recently and welcome discussion. Thanks for your attention.
Thank you so much, Sijie. That was a really excellent presentation. Again, we've got some time for some questions. So does anyone have any questions? Just pop your hand up or unmute yourselves. Helene.
Oh, hi. Thanks again for another interesting talk. So I'm interested in if there were if you were looking forwards into the future, are there different experiments that you would like to see to try and take this forward further?
You mean the time expanding to a longer future?
Yes, yeah.
Yes, and I think the impact of the direct CO2 effect on the subtropical circulation it will show in the first year, but it will not there's no longer change. But for the impact of global warming, it will continue to grow. That means the weakening of the subtropical circulation will continue, and with the increasing of the global warming. Yes, if you continue to extend the experiment time to a longer future. Yeah, thank you for your question.
Thank you. I don't see any other hands for now. So thank you again so much, Sijie, for your excellent presentation.